The last topic here is machines and related topic efficiency. Machines are just devices that can be used to multiply force. Like we saw the ramp in the earlier problem. In order to slide the box up the ramp took less force than if you were to lift the box straight up. That's why we use machines. Now there's always a trade-off. The problem with machines is you get this lower force, but you always have to give something up. We'll see what that is as we look at some examples of machines. We rate how well a machine conserves work by using this concept of efficiency. Efficiency is driven by this Greek letter eta, and efficiency is defined this way. How much work did you actually do, that's called work output, divided by how much work you had to put in. That's a measure of how efficient a machine is. Now a perfect machine would be efficiency of 1. The amount of work out is exactly equal to the amount of work in. But all real live machines are going to have efficiencies that are less than 1. Here are some examples of machines. This is a very simple machine, an ancient machine. This is actually the ramp that goes up to the city of Troy. So the Trojan horse from long ago. Can't draw a very good horse, but that horse is supposed to have been pushed up that ramp. Well, why is that an advantage? Lifting this horse straight up would take a lot more force than getting a bunch of guys and pushing it up the ramp. This is another example of a ramp. This ramp happens to be in City Hall of London. And this ramp goes around in a spiral. So as you go around this ramp, you go higher and higher. But it happens in a more compact space. It doesn't have to be spread all out. Related to a spiraling ramp is a screw, or in this case we see something related to a screw called an auger that moves these balls up there. It's just a ramp, but it's a ramp that spins around. So wood screws and metal screws, all kinds of screws, are just ramps that are wrapped around a center pivot. Another example of a machine is a lever. Here's a person trying to lift up this desk or some large object, and there are two ways you can do it. You can take a pry bar like this and shove it underneath there and just lift up. Well, what you do there is you move over a long distance with a small force because you got a long lever arm, and you're providing the same torque on the other side of this pivot point. Pivot point's like right there. So short lever arm, big force, long lever arm, small force. Same thing over here. Small force here, long lever arm, short lever arm, big force pushing up. That's an example of a lever. It's a machine, and there's a trade-off. The trade-off is you have to move farther with your lower force. Another example is a block and tackle. Block and tackle is just a series of pulleys, and here's how it works. Imagine that you're trying to lift a 100-pound weight here, and you could pull it straight up. That would cost you 100 pounds. You'd have to pull up with 100 pounds. Well, if you took this same weight and you had a pulley and you attached the weight to the string and ran it up over the pulley, you'd still have to pull down with 100 pounds of force to lift the thing. But as you did that, if you moved it a foot here, you would lift it a foot over here. Here's where you can make a machine to minimize the force that you have to use. Imagine that I just attach my rope here. It goes down to my weight, my 100 pounds, comes up, and then here I have a pulley attached to the ceiling, and it goes around this pulley and comes down. Well, now what I've done is, instead of having 100 pounds, I've divided this force two ways. So this weight is attached to a pulley, the string goes around there, and I have 50 pounds on this side, and I have 50 pounds on this side. Well, the tension going all the way around this loop, all the way around that pulley, has got to be the same. It's got to be the same everywhere. So because I divided my force into two 50s, I now have to only pull with 50 pounds of force to lift my 100-pound weight. There's a trade-off, though, and that is that if I want to pull it a foot up, I'm going to have to pull 2 feet of string. I can just keep adding more and more pulleys, and my trade-off gets bigger. I have to pull farther and farther, but my weight keeps getting smaller and smaller. And that's what you're seeing in this picture here. It looks like 1, 2, 3, maybe 5 different pulleys. And so the weight that can be lifted here is going to be much greater than the force that you have to provide when you pull on this end of this rope, but you're going to have to pull farther. Gears are another example of a machine. And you can see what you're doing is it's like a lever. It's like a rotational lever. If I go from here to there, across that gear, it's a small lever arm, so it can provide a pretty big force. Here is a big lever arm, so for the same torque, it's a smaller force. Now here's the trade-off. This thing has to spin faster than this thing. You can see that while this makes one revolution, this thing isn't even coming close to one revolution. So there's the trade-off. There's always a trade-off with machines. Let's do an example problem with a machine. It's a very simple machine. It's just an incline, a slope, a ramp. And the question is, if you have a 21-degree incline, you're pushing this thing at constant speed up the ramp, what is the efficiency? And the coefficient of friction is given as 0.191. What's the efficiency of the machine? Well, first of all, let's set up the basic motion that's happening here. What's the basic work that's being done? Here's our ramp. I have this box, and the box is getting slid up the ramp some distance, let's call it delta D. And it's moving up a 21-degree slope. My job is to find efficiency, eta. And efficiency is the work output divided by the work input. Well, the work output is, what really happens is I just take this box and I move it up to the top of the ramp. That's the work output. I'm going to have to move it a lot further and with less force, but ultimately all that happens is I move it from here to here. So the work output is just going to be equal to the weight of the thing, let's call it Fg, times this distance here, let's call it height, h. But if you think about the relationship between the height and how far you have to push it, height is really equal to delta D times the sine of 21 degrees. So the output work is equal to the weight times delta D, the distance you would push it up the ramp, times the sine of 21 degrees. Now let's look at the input side. To do that, I think I'm going to set up a free body diagram, set this up like a traditional ramp problem, and calculate what is the force that we have to put in. So here's the object being slid up the ramp. It's moving at constant speed. So I've got some force pulling it up. I'm going to call this the input force, because it's doing the input work. Like all ramps, this has got a force normal. The box has got a force restorative here. There's a parallel force, and if it's moving up the slope, there's a force of friction here as well. It's moving at constant speed, so that means net force is 0. So if we take upslope to be positive, that means the input force is equal to the sum of the parallel force and the force due to friction. We know a parallel force is going to be equal to the weight of the box times the sine of 21 degrees. We also know that frictional force is going to be equal to mu times the normal force. But the normal force is the weight times the cosine of 21 degrees. So knowing that, we could say that force of friction is equal to mu times the weight times the cosine of 21 degrees. So that means our input force is Fg sine 21 degrees plus mu Fg cosine 21 degrees. Well, we can take Fg out of here and simplify this a little bit because it's in both terms. So Fg times the sine of 21 degrees plus mu times the cosine of 21 degrees is what input force is. So what's input work? Well, work is always force times delta D, so that means our input work here is our input force, which is Fg times sine 21 degrees plus mu cosine 21 degrees times delta D. Alright, so what's our efficiency? Okay, so what's our efficiency? Well, efficiency is output work divided by the input work. Earlier we calculated that our output work was going to be Fg times delta D times the sine of 21 degrees. And we just calculated the input work to be Fg times sine of 21 degrees plus mu times cosine of 21 degrees, and that was times delta D. Now if you look at what happens here, The force cancels out. The distance you actually push it cancels out. And so it turns out it doesn't matter how big the box is, and it actually doesn't matter how far you push it. The efficiency of this ramp is a characteristic of the ramp itself, not what gets pushed up the ramp. So this is really just equal to the sine of 21 degrees over the sine of 21 degrees plus mu, which was 0.191, times the cosine of 21 degrees. So our efficiency, when you calculate this all out, is going to be unitless. It's supposed to be unitless, and the number that we get is 0.67. Lots of times efficiency are expressed as percent, so you could also say this is a 67% efficient machine.